Welcome to the Explainer. Okay, let's talk about multiplication. You probably think you have it down, right? But what if I told you that the simple way you learned it in school, repeated addition, is actually just the first chapter in a much bigger, way more interesting story?
So let's frame this with a classic classroom debate. You've got student A, who's adamant that multiplication is just adding something over and over again. And then you have student B, who says, no, multiplication is really about scaling.
So before we go any further, who do you think is right? Are you on Team A or Team B? Go ahead, make your choice. We're about to dig in and, well, the answer might not be as simple as you think.
All right, let's start where most of us did, back in elementary school. We're going to look at those first few models of multiplication, the ones where that repeated addition idea seems to work perfectly.
First up, you've got the equal groups model. This is probably the first one you ever saw. 3 times 4? Simple. It's just 3 groups, and each one has 4 things in it. You count them up, you get 12. Easy peasy.
Now hang on, because this is where it gets a little more interesting. We can arrange those dots into a neat grid, an array. And that array model, it very quickly becomes an area model. Suddenly, we're not just counting 12 things, we're multiplying 3 units by 4 units and getting 12 square units. The kind of thing our answer is has totally changed. That's a huge clue right there.
And then there's this one, the tree model. It shows multiplication as this series of branching choices. You start with one trunk, it splits into 3 branches. Then, for each of those 3 branches, you get 4 more little branches. That little phrase, for each, is a massive signal that you're dealing with multiplication. Think about it. How many outfits can you make? For each shirt, you have so many pairs of pants. That's this model in action.
So these models are great, right? They work perfectly, as long as we stick to nice, clean, whole numbers. We've got groups, we've got area, we've got choices, but this is the moment where our simple definitions start to wobble. What happens when we step outside that comfort zone? This is where things start to break.
So, here's the first big challenge. What on earth do you do with fractions? How do you show 1/2 times 8? I mean, how many equal groups is that? How many branches on a tree?
And boom, our favorite model, repeated addition, just hit a brick wall. You literally can't add something to itself half a time. It doesn't make any sense. The model we trusted most has completely failed us.
But wait, the area model can handle this no problem. If you want to multiply 2/3 by 3/4, you can think of it as finding 2/3 of 3/4. It's the area where they overlap. And look at the answer. It's actually smaller than what we started with. Multiplication is now about taking a part of a part.
And that right there shatters one of the biggest myths in math, that multiplication always makes numbers bigger. It's just not true. As we just saw, if you multiply by a number between 0 and 1, the result actually gets smaller.
You know what else breaks the repeated addition idea? Negative numbers. You can't have a negative number of groups. But if you think of multiplication as an action, it makes perfect sense. Multiplying by -1 isn't about adding. It's an instruction. Take this number and flip it over the 0 on the number line. You're changing its direction entirely.
So let's take a step back. Our old models are breaking, but some are holding up. The area model, fractions, negative numbers, they're all pointing toward a bigger, more powerful idea of what multiplication really is, one that works for all numbers.
So here it is, the one definition that holds up through everything we've seen. Multiplication is one number acting on or scaling another number. The first number is like a command. It tells the second number how to change.
And once you get this scaling idea, you get a kind of superpower. You can predict the outcome before you even do the math. Are you multiplying by a big number? The answer's going to stretch. By a tiny fraction? It's going to shrink. By 0? It's going to vanish, collapse to 0. And by a negative number? It's going to flip. That is thinking like a mathematician.
So why is this so important? Because this concept of one thing acting on another isn't just for arithmetic. It's the key that unlocks the door to much, much higher level math. When you get to something like linear algebra, multiplication might mean using a matrix to completely transform a vector, to stretch it, shrink it, rotate it in 3D space. And here's the real kicker. That old rule you learned, that 3 times 4 is the same as 4 times 3, well, in advanced math, that's not always true. Sometimes the order you do things in changes everything.
Okay, so let's pull all these threads together. After this journey through all the different faces of multiplication, what does it really tell us about what it means to think mathematically?
Well, it tells us that being good at math is about so much more than just getting the right answer. It's about being mathematically literate. It's about spotting those code words like of, each, and per that are screaming multiplication. It's paying attention to the units. You know, dollars per hour times hours gives you dollars. The story has to make sense.
And you know what? This isn't unique to multiplication. Its inverse, division, has multiple personalities too. Is 12 divided by 3 about sharing 12 things among 3 people? Or is it about measuring how many 3-foot chunks fit into a 12-foot space? They lead to the same number, but they are totally different stories. Context is everything.
So if you take one thing away today, let it be this habit. Before you reach for the calculator, just stop for a second. Ask yourself, based on what I'm multiplying by, should my answer get bigger, smaller, or flip directions? That one simple question will build your intuition more than anything else.
So we'll leave you with a question to chew on. We just peeled back the layers on multiplication. What other math rules are you holding on to that might just be the tip of a much deeper, more amazing iceberg?